Okay guys, in this video I'm going to cover the 23rd of May 2024 chemistry paper for you. So that's the mock that you may have just sat. So I'm just going to go through each of the questions. I'll explain why the answer is the answer, and what I'd like you to do is to correct the answers that you've got, just to make sure that you're on the same page. So first question is A1, and I'm a big fan of A1, and the way that the word of this question is really good. So it says, alumina is extracted from the ore bauxite, then aluminium is extracted from alumina. Figure 1 summarizes the extraction of alumina and aluminium. So you can see this is the first step. This first step already I can tell is the Bayer process. And this second step here is an electrolysis, and that's the whole row. So let's just label those now. I'm going to call this one Bayer and call this one whole row. The question says, identify which row shows the reaction types that occur in reactors 1 and 2. Already, many of you that do recall this, that the whole row is an electrolysis. So that one's an electrolysis. But this one, we haven't really covered it or given it a name, but I will explain that in a minute. So if you go down to the choices down here, you can see that electrolysis only appears once, and it's C. So the answer must be C. So reactor 2 is C. Let's have a look at reactor 1 though, because reactor 1 says it's a neutralization, and some of you are probably thinking, why the hell is it a neutralization? Where's that come from? So in the Bayer process, what we're doing is we're extracting aluminium oxide, but we're going to use sodium hydroxide as well, and we need to dissolve those as well. So we've got alumina, which is Al2O3, and we've got a base, which is NaOH. Alumina is amphoteric, so it can act as an acid or a base, and in this context, it's acting as an acid. And if we have an acid plus a base, we have a neutralization. And that's why that's a neutralization. Many of you, though, should have just understood that the whole row is an electrolysis, and then process of elimination, the answer is C. Right, let's move over. So figure 2 shows a flow diagram summarizing the steps that occur during the extraction of alumina from bauxite. So this is the Bayer process again. Steps 1, 2, and 3 are the processes that occur in reaction number 1. And they've left these blank for you, but fortunately it's the same 4 steps that I've taught you. So bauxite is ground up into a powder and placed into reactor 1. This is to increase surface area, make it easier to dissolve, make it easier to react. Step 1, what we're going to do in step 1 is we're then going to dissolve it in extremely hot and concentrated sodium hydroxide, which we're going to call caustic. And we call this process digestion. Then that red slurry is going to be transferred into the second step. And for that red slurry, we need to remove some of the metal impurities. So that's our iron oxide that makes it red. And the silica dioxide is going to remain dissolved in there. So we're going to get rid of that in the second step. So that's going to be our clarification step. And in the third step, we need to make sure that we've got the aluminium hydroxide crystals so that we can precipitate them, dry them out in calcination, which is the final step, to then finally get our alumina. So for step 1, it's just fairly straightforward. We just need to find out what this step is. I'm just going to label them here as digestion. Step 2 is clarification. And step 3 is going to be precipitation. The question wants you to write down the number of each step that corresponds to the right step, essentially. So aluminium hydroxide is crystallized. That happens in step 3. That's precipitation. The mixture is dissolved in sodium hydroxide, also known as caustic, and we do that in step 1. And then the metal oxide impurities are removed by filtration. That's step 2, when we remove the iron oxide. Remember, iron oxide is also a useful catalyst in the whole process. Alumina is also used as a refractory material to line industrial furnaces. They want you to give a property of alumina that's important for that use. Many of the common mistakes that I read here is, you read the question as, alumina, one property. You just didn't read the question. The question wants you to know what makes it a suitable use for it to be put inside a furnace. Furnaces are ridiculously high temperatures, so obviously it needs to have a high melting point. Now, whatever's going on in that furnace, whatever's in that furnace, you're not going to want it to react with anything else in that furnace. So you will also need it to be chemically inert. So that is another useful property of it. But you could also say things like the strength is maintained at high temperatures, the strength's maintained at high pressures, it's resistant to corrosion, it's resistant to wear or chemical attack. You could say it's a good thermal insulator, which it is. And in this question, we will accept high boiling point as well. But we're obviously interested in its melting point, not its boiling point. Anything else, though, needs to be ignored, so it just needs to be very, very clear that it's for a furnace. Again, really nice question so far. C, so we're going to go to alumina is added to cryolite in reactor number 2. And remember, cryolite is only used for one purpose, and it's to lower the melting point of alumina. It isn't a catalyst. A catalyst increases the rate of reaction by providing alternate reaction pathway. This just helps it dissolve. That's it. So we're just going to say lowers the melting point of alumina. I'm just going to be lazy and call it MP. Lowers the melting point of alumina. If you said something like, it also allows it to dissolve the alumina, you get a mark for that as well. So dissolves Al2O3, that's fine as well. The mark scheme specifically will tell you to ignore any reference to cost, catalyst, or activation energy because it's completely irrelevant. This question here next, carbon dioxide is formed as a waste product from reactor 2. Describe how carbon dioxide is formed in reactor 2. Again, I actually thought this was a really well-worded question. So if you go back to reactor number 2, you remember it's an electrolysis, it's the whole row. So we have our carbon anodes, we have our cathode lining, we have molten alumina or aluminium in that mixture. We then separate them and we release carbon dioxide gas after a couple of those reactions. What it wants you to do is to explain where the hell carbon dioxide gas has actually come from because we started with alumina. So where we got the carbon from. That's essentially what it wants you to know. So first of all, you need to describe where the oxygen came from, and this is the easiest way to do it. I would just do it as chemical equations. So my alumina, Al2O3, there's the oxygen. I'd try the dissociation for this, Al3 plus and O2 minus. Make sure it's balanced, just for the sake of balancing it. 2 and 3. Here is oxygen. Now that oxygen then will come into contact with the anode. So I would say over here, carbon anode. Some of you already remember where the carbon now come from. But at the carbon anode, what we're going to have is that our O2 minus is going to go and form O2 gas. We need to make sure this is balanced. It's a half equation, so is the stuff balanced? No. Balance on the left, put a big 2 there. Is the charge balanced? No. 4 minus on this side, 0 on this side. I can't add positive, but I can add negative. So I'm going to add 4 electrons onto this side. Again, you don't necessarily need to write a balanced equation. They just want you to know that there's a carbon anode and what's going on. After I've gone through the way that I would answer it, I'll show you what's on the mark scheme. So I've got my oxygen, I've got my carbon anode, and now I still need to explain where that carbon dioxide has come from. So at the carbon anode, this oxygen right here comes into contact with carbon. So I'm also going to do this. Carbon plus O2 goes to CO2. And there's my final answer. You can see that it produces that CO2. Whilst I've got your attention, this also links to A3. So this is the enthalpy of combustion for carbon. It's also the enthalpy of formation for CO2. So just a bit of extra information there for you. It does actually link together. This question doesn't actually ask you to do that, but they could have, and they just didn't. So these are all things that do link together. Now in the mark scheme, the things that they've written for this is that they would accept, and I'll do these in black, that alumina contains oxygen. I'll say O2. Or oxygen is produced at the anode. The electrodes made from carbon, which apparently I've completely misspelled. So the electrodes are made from carbon, made. And then lastly, the carbon reacts with oxygen. And you could say it burns with oxygen because it is a combustion reaction, so you still get credit for that as well. But carbon reacts with oxygen, these are the 3 points they're looking for. I write them in equations because it's just easier for my brain. Right. This is where we bring on to A2. So A2 is some of our organic chemistry. And again, the way that they've written these questions is really, really clever. And I'm a big fan of the way that they've written this particular question. I think it's really tough and you'd have to really know your content inside out for you to actually gain any credit. But they're really nice questions. So chloroalkanes and chloroalkenes are organic compounds that are made from hydrocarbons. Figure 3 shows a displayed structural formula for 1-chloropropane. This can be produced from either propane or propene. Identify which row shows the reagents that react with propane and propene. Now this links back to A2 and the reactions of alkanes and alkenes. Remember, this is an alkane, and one of the reactions that we have with alkanes is free radical substitution. For propene, we have 2 reactions. We've got electrophilic addition, and we also have our free radical polymerization. We're not making polymers, so this time we're looking at electrophilic addition. I'm just going to abbreviate this to EA. In free radical substitution, we need to start with a halogen gas, and then we split that homolytically to form radicals, and then those radicals react in the conditions, and then gives us the things that we need. So, for example, this guy right here. For electrophilic addition, however, we are literally adding our reactants together. So we're combining reactants together. So you need to bear that in mind when you're actually looking for your answer. So in a free radical substitution, we must have a halogen. So for propane, that takes place in a free radical substitution, we must have some form of halogen gas, which means it must be A or B. I'm going to get rid of the options C and D. Now when we look at propene, we're left with 2 other reagents. We've got HCl or NaCl. Now, as far as you guys know, I've never used NaCl to react in electrophilic addition, and I never will. But you have done HCl. Remember, this is going to get added to your propene. And very, very quickly, I'll see if I can show it you. If I go 1, 2, 3, HCl. Double bond breaks, bond to the hydrogen. This bond breaks, goes to the chlorine over here. Now I've got this with a H, double bond's broken, and I have a carbocation there. It's a primary carbocation because it's only next to one carbon group. So it's only receiving electron density from one carbon group. And the Cl has just received a pair of electrons, so it's got a lone pair of electrons and it's a negative charge. Next one we're going to do is we're going to add that right there. And then very quickly you can see 1, 2, 3, we have a chlorine down there. And there is the same as my 1-chloropropane. So that's where that HCl comes from. And that's why the answer is A. Propane will only produce 1-chloropropane under specific conditions. Identify a condition that's needed to produce 1-chloropropane from propane. Propane is an alkane. And to make a haloalkane, we need chlorine, and we need UV light. UV light to cause initiation. It's a free radical substitution, so we need that UV light. So over here, the answer is UV light. Now, a very, very common answer for this is to just generally say the word heat. Now, unless you know the specific conditions, which I haven't taught you because I think remembering conditions is just extra work, they'd only accept heat in the form of temperature, and it has to be over 400 degrees Celsius. So it has to be greater than 400 degrees. So if you say 500 degrees, yeah, great, that's a condition, that's true, that's relevant. They don't accept any reference to pressure, heat, or catalysts just because it's too vague. But the most important one here is actually UV light. Believe it or not, you could also say sunlight. That does give you a mark as well, but I've just taught you UV light. It's just easier to remember. Let's move on. This question caused quite a bit of confusion when I set the question, so we're going to have a look at this in a little bit more detail. Quite a good handful of you recognised how to get the first mark. I don't think anybody identified how to get the second mark, but the second mark is actually much more difficult to get. It says, explain why the carbocation in figure 5 is more stable than the carbocation in figure 4. If you look at figure 4, we got a propane carbocation, and in this one we've also got another propane carbocation, but the cation is on a different carbon, and that will change the stability of it. Remember, when we look at carbocations, there are 3 types that you need to be aware of. I'll draw them here like this. So we can have a carbocation on carbon number 1, have it on carbon number 2, or if we have a methyl substituted, we could have it on carbon number 2 as well. And this increases in stability. And on top of that, we can label each of these. This is on a carbon next to 1 carbon, so therefore that is primary. This is on a carbon next to 2 carbons, so we call this a secondary. And this is on a carbon that's next to 3 other carbons, 1, 2, and 3. So this is a tertiary. And they increase in stability. The reason why is that each of these bonds over here donate electron density to the carbocation, which stabilizes it further. And it's called the alkylation effect. So it's just alkylation, but alkylation is where we have electron density moving towards that charge. So, for the 2 marks, explain why the carbocation in figure 5 is more stable than the carbocation in figure 4. Well, first of all, because figure 5 is a secondary. It is a secondary carbocation. Then you need to follow that up with, why is a secondary carbocation then more stable? It's because more electron density is donated from, I would say, adjacent carbons. I think that's fine. Should I say that? Yeah. From adjacent carbons. I think you would just get the mark, though, from more electrons are donated to the positive charge. More electron density is donated from adjacent carbons to carbocation. There we go. Let's move on. Draw the displayed structural formula for the other stereoisomer of 1-chloropropene. Again, a really, really good question that expects you to know this topic inside out. There's a few things that you needed to be aware of for this question going into it, and they've not even given you any indication of it apart from saying the term stereoisomer. So let's zone in on that. Figure 6 shows a displayed structural formula for a stereoisomer. Stereoisomer is something that has cis or trans. So that means it must have a double bond. Rule number 1, double bond that restricts rotation. Tick. And it must also have each carbon in the double bond has 2 different groups. These are the rules for stereoisomerism. Let's just double check that. Over here, I've got a CC double bond. Tick. In this carbon, is it bonded to 2 different groups? 1, 2. Yes, it is. So there's my second rule. And this carbon is in the double bond. Is that bonded to 2 different groups? Yes, yes. Okay, cool. In that double bond, are there 2 groups that match in the same plane? And yes, there are. I've got a hydrogen in this direction and a hydrogen in this direction. They're in the same plane as each other, so therefore this is a cis isomer, which means they want you to draw the trans isomer. There's a couple of ways you could do this fairly easily. I would just essentially mirror the one that they've got. So they want you to draw the stereoisomer of 1-chloropropane. Go 1, 2, and 3. Keep the double bond in the same place. This time 1, 2, 3. H's go here. I'll just keep that the same, that's fine. This one can go in the same plane, I'm okay with that. Now, I can't draw my hydrogen down here because that's the same as the one above. So, I'm just going to draw it in this angle. And then I draw my Cl. Double check your bonds, make sure you got the appropriate amount of bonds for each carbon. So 1, 2, 3, and 4, cool. 1, 2, 3, and 4, that's fine. 1, 2, 3, 4, that's also fine. Right, now double check the stereoisomerism. Double bond, tick. Carbons have two different groups. 1, 2. Yes, they do. 1, 2. Yes, they do. Are the hydrogens in the same plane as one another? 1, 2. No, they're not. So this is the trans isomer. And then that's how you get your 1 mark. The double bond in the CC is 1-chloropropane is formed using 2 types of orbitals. Identify the 2 orbitals used to form the CC double bond. And in table 2, place the tick in the box next to the orbital. So this again requires you to know your orbitals inside out. So you've got the orbitals here, P, S, SP, SP2, and SP3. If it's a CC double bond, we already know it's SP2 hybridized. Let me explain. So let's go back to this and I'll do it in green. Are they asking for a specific carbon? No, they're not. Okay, cool. So let's have a look at this carbon over here. It's got 3 bonding regions, 1, 2, and then 3. Which means it requires 3 hybrid orbitals. I can make a hybrid orbital using an s orbital, a p, and another p. So s, p, p. Which orbital did I not hybridize? The 3rd p orbital. So this is going to form an sp2, and there's 3 of them. This p orbital remains the same as a 1p. Let's draw our carbon. And let's draw the orbitals around it. sp2's got a petal shape, and p orbitals have a dumbbell shape. Let's add those shapes in. So I'm going to do my sp2 around the carbon here. 1 in this plane. I'll do another orbital in this plane like that. And then I'll do will it let me do another one? Yes, it will. And then I'll do the 3rd and final one in this plane here like that. There's my sp2 orbitals. Now I need to add my p orbital. And this one, I just imagine is a little bit larger. That's a bit too much. And I stick it here just like that. Right. When this comes into contact with another carbon of the same hybridization, so that's this carbon right here. Let's look at this one. It's the same, it's just upside down. So I'm just going to flip it. What type of overlap forms that CC double bond? Over here, I've got a sigma bond, and over here, I've got a pi bond. A sigma bond is head-on overlap between the sp2s, look, and there's the head-on overlap. The pi bond, however, is a side-on overlap from dumbbells, from the p orbitals. So there's my p orbital right here, there's another p orbital right there. They're going to side-on overlap, and that's going to result in a pi bond, which gives us our final part of our double bond. I'm just going to get rid of these, and then I'm going to show you that it goes a blob here. So I've got an electron cloud above, an electron cloud below. And there's my 1 pi bond, and that's been formed from p orbitals. So the question over here is, which orbitals are used to form a CC double bond? A p orbital and an sp2. This forms our sigma bond, this forms our pi bond. And that's where that's come from. It's a really, really tricky question. Many of us did pick up 1 mark. Some of us picked up 2. Really well done if you did. But it does require you to know that content inside out. Let's move on. This question was quite frustrating from a teacher perspective because of the way of it's the way that they structured the mark scheme. It was almost as if they've set you up to fail. I'm not a fan of this question whatsoever. I really, really didn't like it. I think many of us did get 2 out of 4. And for those of you that did get the 2 out of 4, you've answered it beautifully. It's just not a very nice question, but I'm going to explain why. So, figure 7 shows a displayed structural formula of 1-chloropropene and 1-chloropropane. It wants you to explain the difference in bond angle around the middle carbon between the alkene and the alkane. Many of us did the same kind of analysis breakdown that I showed you to do. So I'm going to do that now, and I'll show you where to pick up the marks. For this, I even scrambled. I just saw it was worth 4 marks, and I was thinking, I can't really think of a way to explain 4 marks, so I explained everything I could possibly think of. And then when the mark scheme showed it me, I was like, right, this is really infuriating. So the first thing we're going to do is we're going to look at this particular carbon. We're interested in the central carbon. Central carbon right here has got 3 bonding regions, 1, 2, and then 3. 3 bonding regions. It's got 3 bonding regions, which means it needs 3 hybrid orbitals, which means it needs s, p, p. So I'm going to call this an sp2. If it's sp2 hybridized, it means it must be trigonal planar. And if it's trigonal planar, this carbon has a bond angle of 120 degrees. Let's do that same analysis for this one. I'll keep the same colours. This carbon over here has got 4 bonding regions. 1, 2, 3, and then 4. 4 bonding regions. I'm just going to keep this abbreviated. 4 bonding regions needs 4 hybrid orbitals made up of s, p, p, and p. So therefore sp3 hybridized. Anything that's any carbon that's sp3 hybridized has a shape of tetrahedral. If it's tetrahedral shape, that means as it exists in 3D, it's 109.5 degrees. And there's our bond angle right there. It wants you to explain the difference in the bond angle, not describe it, which is why the question is so difficult. It wants you to explain why is one of them 120 degrees and the other one is 109.5 degrees. Now, one of the explanations that you should all be getting is that it's got 3 bonding regions, so therefore it's 120 degrees, and the other one's got 4 bonding regions, and therefore 109.5 degrees. Many of us picked up those 2 marks. Let me show you how I structured my answer. I'll do this in black. So I've got here my alkene, and here I've got my alkane. Again, the question is difficult because they want you to explain the difference. So for our alkene, I've done something that looks like this. It's got 3 bonding regions. And this one had 4 bonding regions. I know it's not compare, but it is easier to do this way. It's got 4 bonding regions. What I'm going to say is for an alkene, we've got 120 degrees. And for this one, it's 109.5 degrees. So I can see already that this one is bigger than this one. And this one is less than this one. This is where many of us picked up those 2 marks. Now, to get the 3rd and the 4th mark, this is where it gets a little bit sticky. This is something I've explained in my A2 videos, but it's not something I went into a lot of detail with because I never imagined it would come up in the way that they've asked it. So it's very, very odd that the way they've done it. Now, before we do that, let's have a look at this particular carbon. Now, I've said this before, but when we look at methane, why doesn't methane just exist like this? So why don't we just group them all together like that? So we give them all a bond angle of like 10, 10, 10, 10, and then whatever the difference is of that. So why doesn't this exist? And the reason why is to do with this. So a hydrogen over here, hydrogen here, hydrogen here, and a hydrogen here. And what's keeping those attracted to that carbon is these electrons in here. So you've got these electron pairs in here. What do you think these electron pairs are going to do when they come into contact with one another? Electron pair and electron pair, they're going to repel. So they're going to repel each other as much as possible. So this one's going to push it away and go, right, okay, I want to be as far as possible from those guys. Cool, he's done. This guy's also like, well, I've got an electron pair, I want to repel as much as I can as well. So he's going to go there, but he's going to realize, okay, I can't go there because now I'm too far, so I'm going to go somewhere in the middle, like there. This guy's also going to do the same thing. He's like, oh, well, if you guys are moving, let me repel as well. And it's going to repel over maybe in this direction. Because it's a 3D world, this one's going to go right to the back. And that means this guy's like, right, well, you're a bit too close to me now, so I'm going to go right to the front. And I'm going to stick out here. Let me make it bigger so it looks like it's coming out at you. So this would be our wedge. This guy over here, I'm going to make it smaller. This guy would be our dash. He's going in the background now. And that was surprisingly effective, actually. Right. Now what we've done is we're in 3D space. We've got 4 things apart. This now becomes 109.5 degrees. The reason why is because the electron pairs or the electron pairs in those bonds repel each other. That's where that third mark comes from. Electron pairs repel one another. Now, this is where it gets very, very weird, and I'm really not a fan of this question. So, I'm going to delete this. I'm going to get rid of one more carbon. Right. Let's have a look at this where I've only got 3. Wait, let me make sure it's consistent. Let's get rid of that. So now I've got this guy. I'm going to do a carbon. And is that just a CH2? Let's just stick that there. Right. This time, you can see a little bit more going on. So let's do the same reenactment of what I just did before. I'm going to put these guys all really close together like that, and this guy really close together like this. Right, now you can see a problem already. That the shape doesn't look right to start with, but let's have a look at what's happening here. This electron pair is next to a double bond, and there's loads of electrons in there. It's electron dense, it's electron rich. So this is going to repel it as far as humanly possible. So it's going to go, right, I just want to get as far away from that as possible. So it's just going to repel each other to the other side. This carbon-hydrogen bond is going to do the same thing. It's next to a super electron-rich center. It's just going to repel each other as far as humanly possible. So it's going to go to there. This guy's going to move away, and then we're going to get something like this. So they're going to keep kind of balancing themselves out until we get as far as possible for all 3 of them. Now, if we've only got 3 regions of electron areas here, so because of this, we actually the pressure this has to move is far less than the pressure of this one. This one's now stuck in between 2 things. It's quite a tight fit. This one's got a little bit more wiggle room. The reason why is because this has less repulsion in general, so it can maybe move around this area a bit like that, a bit more free than the other one, just like that. And same for the other one down there. The way that they want you to word this is that in this there's less repulsion for 3 bonds than 4. Because there are fewer things. You could also mention this bit. So this is the mark that I got right here. This double bonds repel more than single. I did get this mark, but I wrote it in a very, very weird and wordy way. So this is a much more cleaner way of writing it. But that's where you get that additional mark. So just to zoom out, this question wants you to do 4 things. Identify the fact that one's got 3 bonds, the other one's got 4 bonding regions. One's got a bond angle of 120, which is greater than the bond angle of 109.5. That's fine. The reason why is because these electron pairs repel each other. And if you've only got 3 things, there's going to be less repulsion because you've got less things to repel from. However, one of those things is a double bond. So double bonds repel more than single bonds. And you get a mark for any one of those 2 points down there. So you get 1 mark for that, 1 mark for these, 1 mark for the purple, 1 mark for the orange. But again, I was not a fan of this question. I thought it was a really tough question. Let's move on. Right, so on this side, we've got question number 3, and we've got A3. This is the sulfur trioxide. It's made using the contact process, and the contact process is one of those equations that, for some reason, you just need to remember them. And I've said it in your booklet, just remember this, and it did come up. Table 3 shows the standard enthalpy changes of formation for the substances of the contact process. They're not asking you to do Hess law. Remember, that would be, what is the enthalpy of combustion? Here's the formation data. What is the enthalpy of this reaction? Here is some formation data. Use the elements to work it out that way. But they're not asking that. They're asking for very, very simple, straightforward, what's the enthalpy of that reaction? We've only got these things here, and we've got some data in our tables. It is really, really straightforward. For the enthalpy of reaction, we're just going to use products minus reactants. So I'll write it out for you. The enthalpy of reaction equals the sum of the products minus the sum of the reactants. Quite a handful of us got this. I'm not too worried. So when we sum up the products, SO3 is our product. This is our SO3. And this is the enthalpy of SO3. So I'm going to write in negative 395. I'm going to subtract the enthalpy of my reactants. My reactants there is SO2. I've got an SO2 here. And then I've got the value for SO2 there is negative 297. Negative 297. I would like you all to notice that when I've written this in, I've kept the negative in there. So I've done negative 393, subtract minus, or negative, 297. And some of you have gone really fancy and gone, right, I'm going to turn that into a plus. And then for whatever reason, something's gone wildly wrong and you've gotten the wrong answer. Put this into your calculator exactly as you read it. So negative 395, subtract negative 297. And it will look something like this. When you press equals in your calculator, you should get an answer of negative 98. Yeah, that's right. Negative 98. If you got positive 98, you get 1 mark. This question expects you to understand the enthalpy of formation and remember the definition of it. So it's the enthalpy change when 1 mole of compound is formed from its elements under standard states and conditions. Oxygen, if we zoom out, is a gas in standard states. So the standard state of gas is oxygen. The formation of oxygen is oxygen as a gas. If I go from oxygen gas to oxygen gas, there is no chemical change. So it is 0. The way that you need to say that is, well, oxygen is an element in its standard state. I can show it you. So, chemistry-wise, I've got oxygen gas. And I want to form that from its elements in its standard states and conditions. So, let's form oxygen from its standard states under standard conditions. What elements are in O2 gas? Oxygen. How does oxygen exist in room temperature, standard temperature and pressure? As diatomic molecule, O2, and it's a gas. Right, I've gone from O2 gas to O2 gas. Is there a change? No, no change. So therefore, the enthalpy change will be 0 kilojoules per mole. This is just a little bit of information for you. I know the question says state. I'm just explaining it for you. So that's the explanation. The state of it, state the answer. The answer is simply oxygen is an element. All elements have the formation of 0. Very, very easy. Over here, vanadium oxide is a catalyst used in the contact process. Some of you use my technique where you just spitfire everything to do with catalyst. I love that you did that. However, the exam board seems to be saying, do not do that for this question. And that's fine. The question's only worth 2 marks. Describe how vanadium oxide behaves as a catalyst in terms of electron transfer. So they've been very specific in the way that they want you to talk about it. When we talk about electron transfer, they want you to talk about where is it reduced, where is it oxidized. So you need to make sure you're using those terms. Now, the way that I wrote this was a little bit like the way that it's been written in the booklet. So I'm just going to use the same process. Vanadium oxide behaves as a catalyst in terms of electron transfer. I start off with V2O5. And in the first step, it goes to V2O4. What's happened there? It's being reduced. And what does reduced mean? Gains electrons. Right, the second step is V2O4 goes to V2O5. What's happening here? It's oxidized. It loses electrons. And because I'm picky, I would also say returns to original state. Returns to its original form. So you would get the marks there for reduced, gains electrons, then oxidized, back to its original form, loses electrons. 2 marks. I actually think the red parts are what you get the marks for. But you do need to understand that and you do need to memorise it. Unfortunately, yes, you need to know the chemistry inside out to be able to access these questions. Right, this question. This question doesn't come up very often, and when it does, it's a 4 marker. It's very similar to what you guys do in physics. So there's not much time that I spend on this question. It's a very much straightforward rearrangement. It's just maths. Put the numbers in, get the numbers out, and you're done. Right, let me break it down to how I would do this question. Maybe it's similar to the way that you would do it, maybe not. Very few of you rearrange this incorrectly by starting to divide instead of subtract. Let's just look at the equation to start with. Again, when it comes to math questions, I always rewrite the equation before I even look at anything. So delta H equals delta U plus P delta V. Yes, I already know it's there. Now my next step, I'm just going to substitute the values that I can see. Let's have a look at what we've got. A sample of gas from the contact process is allowed to expand into a storage container. The data is collected below. Heat energy is 1.25 kilojoules. I can see a kilo there. Maybe I need to convert it. Let me look at my final answer. It's also kilojoules. So I don't need to convert anything there just yet. So I've got kilojoules, 1.25. I've also got delta U. It wants me to actually determine delta U, so let's just keep that as delta U for now. Plus P delta V. Do I have a P value? Pressure is down here, is 200 kPa. And that is also in kilos. That's in kilos. They're gonna basically maintain the same, so I don't need to do actually any conversion here either. Some of you may converted this, and I believe you'll lose 1 mark if you converted this. If you converted it, then this answer here would be in joules, and you would need to convert that as well. So I'm going to use 200 and keep it in kilo. I'm going to multiply that by my change in volume. Do I have a change in volume? All right, I've got an initial and I've got a final. So I've got 5 times 10 to the negative 2 and 7.5 times 10 to the negative 2. These factors are the same, so it is basically just 7.5 take away 5, that's 2.5, times 10 to the minus 2. So I would do that here, just to show that delta V equals 2.5 times 10 to the negative 2. And that is in meters cubed. 2.5 times 10 to the negative 2. Right, there's some things here I can do to simplify these down. Let's go down here and do it like that. So I'm going to do 200 times 2.5 times 10 to the minus 2. 2 times 10 to the minus 2, that cancels. 2.5 times 2 is 5. So I'm going to do delta U plus these two put together is going to give me an answer of, let me do it in orange, is 5, equals 1.25. Right, now I've got some basic rearrangements to do. I need to make you the subject. Sounds funny saying that out loud, but I need to make you the subject. And at the moment on this side, it is attached to a plus 5. How can I remove that plus 5 from there? Some of you guys are a little bit more familiar with this system, so I'm going to subtract 5 from both sides. Subtract 5 here, subtract 5 here. This will give me this there, like that. And then these two would cancel out. And that's how I would rearrange it, like that. Some of you don't like that method, and that's fine. The way I would do it is I see it as I move things onto the other side. I need to move everything away from delta U. Delta U is currently being attached by this. So I'm going to move that onto the other side. When I move it onto the other side, I can't move it over like this, because that doesn't look right. I have to move it over like this. So there it's going to go. So let me duplicate this line just so you can see it. So I'm just going to subtract 5. That moves on to the other side and becomes a subtract. And now I've got my answer. So 1.25 subtract 5 will give me negative 375. and that's going to be in kilojoules, and that's absolutely fine. I'm going to shrink that down to fit. Kilojoules, and then I'll double underline it to show that's my answer. Some of you guys just need to practice rearranging, but that's the way that I would do it. Right, let's move on. Question 4, sorry. Question 4, we're now linking back to electrophilic addition. I'm going to the hydration of ethene. Remember, this is just an electrophilic mechanism. I have taught you the electrophilic mechanisms. I just don't call it the electrophilic. I just don't call it hydration of ethene. It's an industrial process used to make ethanol. In step 1, ethene reacts with phosphoric acid. Again, I've not shown you this, but the mechanism is the same. And in step 2, the carbocation reacts with water. That's okay. Let's break this down a little bit further. So, the letters X and Y in step 1 and figure 9 show the position of the curly arrows that should be included in the mechanism. Identify which row shows the direction of the curly arrows, X and Y. Right. Let's just zoom into this mechanism and complete it ourselves anyway. Right. Some information time. This is A2, electrophilic addition mechanism. Let's talk about that. Right. Over here, I've got a region of electron dense. So it's an electron-rich center. Right, it's an electron-rich center. And then over here, I've got a delta positive hydrogen, and I've got a delta negative oxygen. This delta negative oxygen over here. This means this is a polar molecule. It's a polar molecule. And this is going to be an electrophilic addition, which means that this is our electrophile. It's got a region of positive, and it's attracted to a negative. And then and then this is going to form a covalent bond by donating a pair of electrons. So let's have a look at that step by step. Our electrons here are attracted to the delta positive hydrogen. So from the bond to the hydrogen. Now that bond is going to form a covalent bond between the carbon and the hydrogen. This double bond here is going to break. The pi bond in that bond is going to break. And it's going to break in a heterolytic fashion. So it's heterolytic fission. This bond means that this bond here, the two electrons here, they're also going to break. And both of those are going to go to the oxygen. It's electronegative. It's more likely to attract a pair of electrons. So it's going to pull those in. Now, the next step, you can see hydrogen is bonded to there. We've got a carbocation being formed here. And this guy is now gone off and done its own thing. That's doing its own little mechanism. That's okay. But what we've got here is the water that's come in, uses a lone pair of electrons and bonds to there. That breaks this bond here. And then we finally get our alcohol. Right. Let's go back to the question. Questions wants us to draw the arrows of the curly arrows for X and Y. Remember, curly arrows is a movement of a pair of electrons. The pair of electrons in the double bond go to the H. It means we're going downwards, which means it can't be this one or this one. But it could be C or D. Let's have a look at Y. Y, this time, we've got a single bond there is going to break, and the electrons are going to go to the oxygen in the phosphoric acid, which means the arrow's going downwards. So it can't be this one. And, well, by extension, it can't be this one either. So the arrows are going downwards, so it can't be this one either, which means it must be D. Give yourself a tick. And that's why. Let's move on. This question, in step 2, the carbocation acts as an electrophile. Describe how figure 9 shows that carbocation is an electrophile. Now, when I first read this question, I thought this is actually a fantastic question for you guys to link the information that you know between carbocations and electrophiles. The fact that it wants 3 marks from this, though, confused all of us. It's very, very difficult to explain this in 3 marks. And I believe when I attempted this, I got 2 of the 3 marks because the 3rd mark is just almost nonsensical. But throughout my entire chemistry career, when you talk about an electrophile, it's just something that receives a pair of electrons. So it's an electron pair acceptor. That's it. So I'm not really sure where else they're going with this. But let's talk it through. It wants you to explain why a carbocation acts as an electrophile. So let's have a look at a carbocation first of all. So I'm going to draw one in. to help explain this. Right. Carbon-cation, what you can see over here is it's got a positive. Why would that positive make it an electrophile? So let's explain that point in blue. The reason why is because it's electron deficient. So I've got an electron deficient sensor. Or an electron deficient carbon. And you can add to this and say it has a positive charge. It has a positive charge. So it's an electron deficient carbon and it has a positive charge. Cool. The next step is if it's got a positive charge, what's it going to receive in order to neutralize that positive charge? Well, it must be a pair of electrons. So it's an electron pair acceptor, and accepts a lone pair of electrons to be more specifically. I would say here, accepts a pair of electrons. So it's an electron pair acceptor. It's a pair of electrons. Now, truthfully, these are the only 2 marks that I actually gained. Because for me, that is what an electrophile is. It's something that's electron deficient and accepts a pair of electrons. That's it. The 3rd mark, after looking at the mark scheme, is because it forms a covalent bond. So after it's accepted the pair of electrons, it then forms a covalent bond. Which is true, it does. It's just not something that's ever really mentioned or said. So it's not wrong. It's just a bit odd that that's the 3rd mark. And that's the only 3 marks they'll give for this question. I expected many of us to get 1 mark. The accepts as a pair of electrons, it's a lone pair acceptor. Or that's the one I expected from you. I think a couple of you said that it was an electron deficient. So really well done for that. Nobody mentioned that it forms a covalent bond because the question doesn't set you up for that. But getting 2 out of 3 on this is brilliant, so I wouldn't worry too much about that. If it comes up in future as a 3 marker, we kind of know what to say next time. Speaking of things that are kind of out of pocket, this is something that in the, how long has it been running for? 8 years? In the 8 years of the triple applied science, they've never asked for the conditions of the hydration of ethene. They're just 2 numbers that you need to remember. And again, you already have so much to remember that's worth so many more marks that this just isn't one of those things that I throw at you to remember. If you do enough past papers, after doing this one, you'll realise this is one of the things that you just need to remember. There's no way for you guys to work this out or to understand it. There's nothing special about that. It's as simple as just saying, right, I want you to remember these figures. I remember this from when I did it, God knows how many years ago. I just know that the temperature is 300 and that the pressures, in my head, it was pressures between 50 and 75. So the only number for me was 70. And I did get this right. So the pressure's 70 and the temperature's 300. You just need to remember those 2 numbers. Terrible question, worth 2 marks. It's also essentially multiple choice, so you can just guess. Let's move on. Right. Speaking of horrible questions, question number 5 is a 6 marker that wants you to recall as much information from Unit 1 as possible and link it to Unit 5. So it's a really, really, really tough question. Table 4 shows a standard enthalpy change of hydration for some common ions. You've got a list of positive ions over here going across a period, and you've got a list of ions over here going down a group. Some of you may have realised that when I framed it that way, that they want you to remember charge, attraction, radius, and shielding. This question is actually about charge density and how that links. It's a very, very tough question. But there are some things that you can do to pick up some marks quite easily. Let's talk about those first. Discuss the standard enthalpy change of hydration shown in Table 4. Your answer should include the meaning of the term standard enthalpy of hydration. So there's those 2 marks that I told you to revise in class that they'll always come up. And the factors that affect the size of the values. This is where you need to relink back to Unit 1 of charge, attraction, radius, and shielding. Not necessarily in that way, but I will explain it. Let's start off with the most easiest way to pick up those 2 marks, the definition. So define enthalpy of hydration, HYD. The enthalpy change when, write the count 1 mole of isolated gaseous ions is dissolved to form 1 mole of aqueous ions under standard conditions, not states. I think if you've written this definition verbatim, I will give you probably 2 marks for that. There's another thing that you could probably get credit for is this, and it's stating the standard conditions, so 298 Kelvin plus 100 kPa. I wouldn't give you a 3rd mark for that, but it would solidify that 2nd mark for you. And the other thing that you could mention that is in the mark scheme, but it's just not something I ask you guys to recall or know, but forms an infinitely diluted solution. Yeah, so you could also mention that as well. I'm not a big fan of remembering that as the definition because the first 2 points cover it enough. So that's your definition for your hydration. Now, there's a few more things that I want to talk about before I go into talking about these. Now, when I answered this question myself, I went straight into talking about charge density and about these numbers, charge density and these numbers. However, just so I can teach it you and go through it a little bit more clearly, let's talk about the enthalpy of hydration first, and then I'll explain that point. I'm going to title this part hydration. So we'll call this hydration. And it's unlikely you'll ever write it in this order. This is the order of the mark scheme, but this is something that I did at the very end of my question. So for hydration, we need to first of all understand why is it that all of these values here are exothermic. That's one thing they all have in common. So you can discuss that as a point, and I believe I would give you credit if you've written all are exothermic. Let's explain why they're exothermic first. So for hydration, what we're doing is we're dissolving gaseous ions into water to form aqueous ions. Did I mention water over here? No? See, now I've said it out loud. I forgot. Is dissolved in water, in H2O, to form 1 mole of aqueous ions under standard conditions, right? So for hydration, we need to understand, first of all, about water. So water, I'm just going to draw in black, OH2, just hid like that. Now, water is a special compound. It's polar, which means it also experiences things like temporary dipole-induced dipole forces. It experiences permanent dipole-dipole interactions. And it also has H bonding, which is an extension of PDDI. Has H bonding. The reason why it's got H bonding is because this OH bond over here is polar, which means there's a large difference in electronegativity. Remember, hydrogen's in group 1, oxygen's in group 6. They're very far apart on the periodic table. There's a very large difference in their ability to attract a bonding pair of electrons. So the way that we show that is that oxygen is going to be delta negative and hydrogen is going to be delta positive. So is this one over here. So these are delta positive, they're delta negative. Right. When we're going to dissolve ions or some form of salt, but in this context ions, into water, they're going to form a bond with that water. Let me explain. So let's have a look at one of these ions over here. Let's look at sodium. Let's do an Na+. I can do a Cl- as well, just for the sake of drawing one. So I've got Cl- there as well. All right, for the Na+, the sodium plus, this is going to be attracted to the water. And not just any part of the water, it's going to be attracted to the delta negative in water. Not negative, because it's not an ion, but a positive ion is going to be attracted to the partial negative oxygen, like this. Right? And because of that attraction, that's going to form a bond. Bond forming is exothermic. So over here, I'm just going to write bond forming is exothermic. So whenever we form bonds, we release energy. Cool. So releasing energy is going to be negative. So that's where that negative value comes from in our data. Now we've got a chloride. Chloride is also going to be attracted to water, but a different part of it. Chloride is a negative ion, it's an anion, and it is therefore attracted to the delta positive, partial positive hydrogen. And that is also going to form an interaction here. That interaction is bond forming and therefore exothermic as well. So there's those exothermic reactions. So that's the reason why it is exothermic. Now, the way they're attracted to each other depends on how much charge that you have. If it's got 1 plus, it's going to be slightly attracted to that delta negative. If it's 2 plus, 2 positive, it's going to be way more attracted to that delta negative. And the more attracted it is, the more powerful that bond forming is, and therefore the more negative it is. Same for Al3+. When you look at the final column of these group 7s, they're all 1 minus. I've got chloride, bromide, and iodide, negative, negative, negative. However, they're not the same because you can see that they become less exothermic as we go down group 7. The reason why what happens is when we go down group 7, we have more shells, more shielding, more electrons. The atoms become bigger and bigger and bigger. Therefore, the ions are bigger and bigger and bigger. And we still have the same negative charge. So as we go down group 7, the charge density decreases. Because the charge density decreases, there is less attraction between that and the H2O, and that means it becomes less exothermic. When we look at the positive ions, you can see that we're now going across a period. We're going from group 1 to group 2 to group 3 metals, and as we do that, they become more and more positive. Because they're becoming more and more positive, but we're keeping the amount of shells the same, they're going to be more closely attracted. So the charge density increases because we're getting more and more positive, but we're not actually adding any more shells or any more shielding. That's staying the same. So those shells or those electron shells are now being pulled in more closely to that nucleus. So they're getting smaller and smaller and smaller and more positive, more positive, and more positive. So by the time we get to Al3+, it is a tiny ion with a ton of charge. It's almost 3 times the amount of charge of sodium, but it's smaller, so it's going to be even more attracted to that. And you can see that with the exothermic results. It gets significantly more exothermic as we go across that period of ions. Na+, Mg2+, and Al3+. And that's what this question wants you to discuss. Let's put some of those things into words so you can understand it a little bit more clearly. So I'm going to call this cations. Cations across a period. The main point I'm interested in here is as we go across a period, charge increases. As that charge increases, shielding remains the same. In fact, let's just do it like cars. So C, charge increases. A, attraction increases. If my attraction increases, I'm pulling all of that atom closer together. So therefore my radius decreases. They get smaller. And then the shielding is going to remain the same, which means my charge density, the amount of charge per size of ion, charge density increases. If the charge density increases, this means stronger attraction, between, I'm going to say ions and partial charge or partial negative of water. Which means stronger bonds formed. And if the bonds are stronger, it's going to be more exothermic. What a terribly difficult question for you guys to get. So it becomes more exothermic. Let's talk about anions. Oh, I don't have enough space. I'm going to make another page. Let's duplicate it, yeah. And this isn't because the question is so difficult you needed so much space, it's because I'm explaining it to you guys and writing loads. So, anions. Across, anions down a group. Anions down group 7. So let's have a look at this again. Let's do charge, attraction, radiation, shielding. Do cars again. So charge down a group. Charge down the group is the same. The attraction is going to be less. The radius increases because there's less attraction. And the shielding increases down the group. Now, normally when I teach this in Unit 1, if it's going down a group, I start at shielding and go up here. So shielding increases. If I'm adding more and more shells, electron shells, the radius will increase. If the radius increases, what's happening to the attraction between the nucleus and that outermost electron that's left? That is going to go down because it's becoming further and further away. So therefore, attraction goes down. And charge going down a group is all going to be the same for ions. So as you go down for the group for ions, they're all going to be 1 minus. So because of this, my my charge density decreases. They're bigger with the same amount of charge. Because they're bigger with the same amount of charge, this means there is less attraction between anions and water. In fact, the delta positive hydrogen in water. Less attraction means weaker bonds, which means less exothermic. And that's what this question really wants from you. Let me just double check the mark scheme. Is there anything I missed? No. No. Okay, cool. So what we're looking at here is we've got define, get your definition in. The hydration part is just for me to teach you and explain it, but if you've mentioned anything about the actual hydration and how it works, you get loads of credit for that. The main question though, however, wants you to explain how cations across a period becomes more exothermic, which is this part, and how anions down a group, this part, also become less exothermic. This, guys, was a really, really tough mock paper. So please use this as part of your revision because there's a lot of things that it covers, especially in your Unit 5. But otherwise, guys, that's probably the end of the video, and I'll see you guys soon. Peace.